Time for another draft physics, draft science here on YouTube video presentation. This basic video, going over the fundamental elements of charge and magnetism. They're very related, and conventional physics really doesn't give you any mechanical explanation. Nothing they could draw without citing something like, and then the gremlins, or then the pixies, or the angels, or the magic force does the magic thing that makes it happen. So they can tell you that, like charges repel and this kind of stuff, but they can't tell you anything about why that happens at all. They just have nothing. They say something like virtual photon, which just means basically that yes, it moves the speed of light, it moves the speed of force, this messenger that says come to me or run away from me, but they don't really define the messenger in any other way. It's got no definition at all. And like in gravity, where they say the space tells the matter what to do, it's the same empty kind of answer, and yet people are quite satisfied that they've explained it well enough. They've told you what it will do, and therefore that's all you need to know, and we really don't have to do this worrying about mechanism or real causes or really understanding it in any kind of real way. Just understand it as, yes, some of your socks disappear. You put them in the dryer and they disappear. That's it, right? So there's just no explanation, and so we're just supposed to blame whatever, anything. I'm arguing that yes, that can be understood mechanically. There are models that get close to, if not very close to, the truth. And physics won't consider them because those models will limit how much of their entanglement and fun things are permissible. So anyway, but to start, I have to say something negative about Google, because it does censor my videos. It does force me to speak differently than I would speak, and it does so in an arbitrary way, where it just basically says certain kinds of people we don't like. They're cranky, or they're not fun like us, and so we will discriminate against them. And certain people we will give the right to censor other people, and certain people won't. So depending on how much clout I have on YouTube, if I don't like something, YouTube will make me happy. If I don't have any clout, if I don't have a lot of subscribers, then it won't pay any attention to what bothers me. It's totally discriminatory in its practices. And just as a throwaway comment, we'll add to the evil statement, that they promised us this non-commercial alternative. They clearly intended to make it a commercial alternative, put ads on other people's website. That was the plan. So they lied about their intentions. Don't be evil was their slogan, and they had every intention of being evil. And on top of that, we don't even get what we were promised in the simplest sense of Google puts ads in the search results, the actual search results, which is something the other search companies couldn't get away with back when there was a competitive market. No competitor in that market could get away with that because it was really frowned upon. I mean, you either have your advertisement, but don't try to hide an ad as a search result. That's really, that's cutting too much of the corner. And now Google gets away with it without anybody even peeping, because it's bought all the complainers out of existence. And it's the same thing Microsoft did in terms of, if somebody's making negative noise, bribe them to shut up, and if they're competing, then buy them to stop doing that. And that's all this is. It's just the worst of corporate America, and Google is a perfect example of the absolute worst of letting corporations control any part of our infrastructure at all. Bad idea. Alright, so on to the video. So, the simplest way I can tell you to understand this, or attempt to understand, is something as simple as light. It's around you all the time. Light bulbs obey the inverse square law, and this is a fundamental rule for all radiation emitted by objects, is that they tend to radiate this stuff, okay, over a period of time in all directions. So one minute they might shoot something this way, the next minute that way, the next one this, and it all ends up being a consistent amount over a whole range of vectors or directions. And as you go with distance, those things are separating because they start at one tiny little point. They have to separate as they go out, and they separate in 2 dimensions. So they get further apart this way and further apart this way, and that's the inverse square law. Alright, so if you thought of it as a little paintball machine, you know, it's just shooting little dots of paint, you can understand the closer I am to it, the more little dots of paint that are going to hit me. The further away I get, the dots get less and less regular. I get fewer and fewer bits of spatter that reach me. That's the inverse square law. It's not a mathematical concept. It's a physical, real concept. And the math can describe it. The math didn't create it. It's not made of math. It's made of a physical circumstance of having 3 dimensions that things can move in. And it's quite critical to understanding. Also, light provides us an understanding of color. And so we can understand that you can have red stuff and you can have blue stuff, and you can mix them and it'll be purple stuff. And so if you thought of objects being able to reflect red, and that's all they reflect, or they just reflect blue, and you could hit them both with white or purple, and one of them would be blue to you and one of them would be red to you. So if you can understand that, you can sort of understand what charges are doing. So I shouldn't have to go into any detail on the existence of these concepts of an electron and a proton. They're sort of the elemental charges, the elemental mechanisms of the function of charge, and that's the concept of plus and minus. Now, some people will say this is an arbitrary distinction, calling them plus and minus. Well, it's clearly not, in the sense that you could call them up and down, or strange and weird, or strange and regular, but that really wouldn't be telling you something, because it really is a kind of a quantity of something, and it's a distinction. Now, if I called them red and blue, I suppose you could understand that those 2 things are inverse colors. You could, you know, but you really have to understand their inverse nature, that blue is fundamentally different than red. And then when you're talking about a charged objects, you know, like I put a charge on something, you're really just talking about adding and subtracting electrons. So you're just really talking about, I can make it positive by putting, you know, taking electrons away, and I can make it negative by adding electrons. And so it's a subtle bit of the mechanism that does make it a little confusing, but the elements are distinctly inverse in their function. So anyway, electrons will do exactly the opposite of what a proton will do in the same environment. So if I create an environment of, say, purple, the purple will do to these 2 things the same thing, in the sense that whatever there is in the purple, both of them will say it's nothing to them. Okay, but if I make it a red field, you know, in this case, let's just say white is red and green is blue, you can see some distinction there. It'll have to be enough of a distinction, frankly. So if I hit it with red, the red object moves away. If I hit it with red, the green object moves towards, and that's the inverse relationship. So regular physics just doesn't say anything about that. And obviously, if I hit it with a blue field, a green field, well, maybe let's say green and white. I mean, I can't make purple out of that. Well, whatever. Just, you should be able to understand the analogy. Okay, so I'm not going to push it any further. If I hit it with the green, you could understand that the exact opposite would happen. The electron would move towards, the proton would move away. Alright, so the nature of the charge is basically that it's just radiating. So if I hit it with something, the idea is the only stuff that will reflect off of it is the one color. You know, so it's always radiating this color, and the white is always radiating or reflecting the white color. So you can understand that whatever hits it, the white stuff reflects, and some other, if I hit it with the green stuff, okay, it doesn't reflect, it doesn't create momentum. Alright, it's not the most perfect way to say it, so I'll redraw it and state it more simply in terms of understanding the difference in the momentum. Alright, the thing I want to stress is that it's all straight line force. So the thing would be is that if an electron is sitting in space, the idea is that space is constantly hitting it with purple, okay, with both forces, and from all directions, and we're seeing what the electron reflects, what goes in and then what comes back out. So if I had a field that was just purple, that is, it was full of just green and white stuff just from every direction, it would look to every object, even you, if you were sitting in that universe, like everything was just coming right for you. The only stuff you would see, or the only stuff you would interact with, is obviously stuff, no matter where it came from, that was heading right for you. You'd only interact with a world that everything from every direction looked like it was pointed right at you, just like you were the opposite of a light bulb. Everything would just be hitting you, and if you're a light bulb, you'd be shooting out everywhere. So that's the way it would be. That's the physical fact. Okay, so everything is going to reflect. If it was just a mirror, if an electron was just a mirror, it would look like the light is always on, because whatever's hitting it would be reflecting back out of it. And the only catch is that this purple stuff comes in, and for the electron, and the, if a white piece hits, red, it just reflects. And if a green thing hits, the catch is that it leaves in a different direction. So the idea perpendicular. Now, if the electron was alone in the universe, right, that's not a problem, because it's going to be radiating just as much purple. But it's just the purples come out at a different place, a different location. But from looking at it, it's not going to look any different, except for the light that comes from some directions will be invisible from other directions. Okay, so it's only until you add something else to the universe. So if I have nothing else in the universe, this just reflects essentially purple. Just because this one, the fact that this one went in this way and diverted this way, just means that this one will come in this way and divert this way. So every location will have green and red, green and red. I mean green and blue, red and blue, red and blue, or green and white, green and white. So it would look perfectly the same, all right, but mechanically it's functioning different, and that's the part that matters. So if I have an electron, and now I put another electron in the environment, okay, and they both look like they're reflecting the same world, well, they're really not, because of that change in the fact that the direction matters now. So they would be sitting here, and you could understand that as the universe hits them, the stuff reflects and changes its direction, the green stuff. And so if green stuff comes in this way, it would end up going this way. And then what would happen to it when it hits this electron? Well, then it would end up going this way. Okay, and so it wouldn't exist anymore in terms of being relevant to the electrons. But you can understand that the white stuff, any white stuff that was in this, as they move towards each other, you can't eliminate the universe that was already between them. So any white things that were going this way will just keep doing that. They'll just keep bouncing back and forth and back and forth and back and forth. And you can understand that if with each hit they're adding momentum, that would mean that the two electrons will move away from each other. So now we have change. Now we have electrons behaving in a certain way because of the simple little mechanism, the rule. So the reflections will just add up to more interactions, which ends up being more energy in a sense. So it's just a simple ping pong paddle argument. If I have a ball with perpetual energy between two ping pong paddles, you can understand the further away they are, the less times they hit the paddle, and the closer they are to each other, the more times they hit the paddle. And if each time they hit a paddle they add a certain quanta of momentum, that's going to be more pressure. So the electrons will move away from each other. Now if I take that scenario and I put a proton in the vicinity of this electron, now all the energy that goes in, that's trapped between them, okay, if it's a piece of green energy, yeah, it can reflect off of this, but then when it reflects back, what's going to happen is it's going to leave perpendicularly. So it's not going to be relevant anymore. So it's going to be gone as a piece of energy. The ball is going to escape from between the two paddles. And the same is going to happen even if I have a white piece that go up here and reflect, but as soon as it hits the proton, it's going to go out. And I probably should just draw it as the opposite direction, just to be technically more correct. And it's going to leave in the other dimension. It's going to move perpendicularly. And so now you're going to lose that piece of energy too. So you're not going to be able to trap any energy here and have very low pressure. And obviously the rest of the universe is still hitting it this way. So you can understand nothing's hitting it this way. Something's always hitting it this way. The two things are going to be pushed into each other. And that's basically the elements of charge. So you can have a very simple mechanism that if the thing is alone in the universe, you'd never see it. You'd never know it was charged. And as soon as you bring another object into range, then you can see the charge. You can see that the two electrons will repel, and you can see that the proton and the electron will attract, just because of that simple mechanism. The simple difference between, you know, a white piece of energy hits this and it leaves this way, a green piece hits this and it leaves the other way, and the inverse would be the same color hits and it reflects. Okay, and so the understanding is that every time something hits, it causes momentum for the object in the direction. But when the opposite force hits, the direction, just like the change in the direction of the force, the change in the direction of the momentum is also in the other dimension. And so that can be used to overcome what's called drag, in terms of the fact that things lose momentum with velocity. The faster you move into a force, the more the force is going to affect you in that direction and slow you down. And that can be overcome by creating a little motor out of these parts, but we'll get to that in a different video. Alright, so regular physics doesn't have a mechanism like this. So this is a pretty simple mechanism. It explains why things repel and why things attract. And all you have to believe in is that there's a lot of this force stuff that we don't know about. So we know about cosmic background radiation. There's a certain frequency of that's the dominant frequency. The cosmic background radiation has lots of other frequencies in it. You know, bigger, longer photons further apart. So if the microwave was this, there's still a lot of other radio type waves, and there's other kinds of heat, infrared radiation and other kinds of radiation that's in the universe that we can measure. We can see it. And the point is that some of it we don't see, just like some of the photons. A frog will see more light in a room than you see, because a frog can see photons we can't see. Photons that are structured in some way different, like if this was a photon, in terms of it has a certain number of bits in a certain arrangement, and I would argue that it's polarized, and this would be how you would represent polarization, as just the fact that they're a slight bit out of alignment. So they're all running parallel, they're all moving parallel, these little bits of force, of momentum. And to me, that's an easy way to understand a photon. So it's a very small thing. So this is very thin. It'd be like a piece of paper, a rectangular piece of paper, very thin one way, very wide another way, and it has a length. And you could just argue that frogs see photons that are this big, and we can only see photons that are, rays that are this big. So our instruments would likely have the same kind of limitation. You can take a photo multiplier, a photo detector, and you can turn up its sensitivity. And when you turn it up to very sensitive, it starts picking up photons everywhere. No matter what you do, you can put lead around it, you can put lots of stuff around it, and it'll still click, it'll still go off now and then as something's still hitting it, something's still moving its electrons. And that would indicate that there really are these very small bits of energy in the form of little quanta. And maybe our photodetector can detect ones that have 3, but that doesn't mean ones that have 2 don't exist in the universe, or ones that are all by themselves don't exist. So you can understand that there can be a lot more of this energy we say is around us right now than just the stuff we detect. The stuff we detect just says, what can our detectors, what's their sensitivity? It doesn't mean it doesn't exist in a smaller amount that we don't have any way of measuring. So it's pretty easy to imagine a universe that's more crowded than even the universe we're living in. I mean, right now there's radio waves going through you. There's microwaves. There's all kinds of radiation from all kinds of cell phones. All kinds of sources are hitting you with energy all the time, constantly. And so just multiply that and realize that there's more than just the light you see. There's the light you don't see. Right now, when the light is on, it's sending infrared radiation that's hitting you that you don't see. It's sending ultraviolet light that you don't see. There's even a few X-rays mixed in that you don't see. All right, so that's all that you need to understand. So these protons and electrons are constantly in those environments, and they're constantly being bombarded by energy. And the fact is that all I have to really do is produce more energy in one direction, okay, more force, more stuff moving the speed of light than is coming in the other direction, and the proton and the electron will move accordingly. They will change their position because of these simple rules. But it has to be the right kind of energy. If I want to move electrons, I have to hit it with electron force. If I want to move them in the same direction of the force, obviously. If I want to move them in some other direction, well, then I can hit them with more energy. That's the proton energy, you could argue. But that's not, we don't have guns for that. So it's not as easy to do. So just like charge is always on an object, you're really just talking about how many electrons, how do I change the electrons, the number? And that makes something charged or uncharged. So I take away electrons, I make the protons stronger. I add electrons, I make the protons weaker. That is, the negative charge dominates, or the positive charge dominates, or I can have exactly the same equal charge. And we'll call it a neutral charge then. But I'm really just manipulating electrons. And so the universe really runs on manipulating electrons, because protons are a tiny part of the nucleus of an atom. It's the atom is really about the electrons on the surface, and they sort of dominate. Now, how big are electrons? I mean, obviously we hit them, so they can't be too tiny, because the force hits them and it runs in a straight line. And I guess that's the part I really want to get to. So let me get to the filtering part. Alright, so without going into atoms and the fact that you can manipulate the shape of an atom and therefore make it look more purple, or make it look more blue when it's red, or change its color, so to speak, by changing its shape, changing what it's reflecting. And that's basically what's happening inside of a magnet, is that you're taking a substance that's already magnetized, let's say, And it means it has atoms that are basically following the rule. That is, they have the electron and the proton in such an arrangement that when the white stuff comes into the proton, it always goes that way. So it comes in this way, it goes this way. If it comes in this way, it goes this way. Alright, so you can sort of understand that the inverse is happening when any of the proton energy or the blue light hits. The blue light goes this way. Alright, comes out here, comes out here. So then you can understand that all the reflections from the white would still be straight back. So all those reflections are still going the same way. And so this end will just keep radiating all red, and the other end will radiate all green, or blue in this case. And that's all a magnet's doing. It's just a big filter. So regular physics, they'll give you arguments about, that it's somehow generating fields that are moving around the magnet, and there's stuff moving on these field lines and doing all of this stuff, and all this energy. It's creating a bunch of stuff, and especially a lot of the dissidents have all kinds of theories about all kinds of motion. They'll say that there's some there's ether swirling and swirling and swirling, and somehow the magnet's making all of this energy and causing all of these orbits. Like somehow it's causing something to bend and curve and do all these shapes. The simple argument is no, it's just straight lines. Okay, the curved line is just made out of straight lines. That is, there's a certain amount of force coming off of this, and there's a certain amount of force coming off of this. And in this case, the longer the line, the weaker the force. And so you can sort of understand that at every point, there would be you could find points where it's always equal. That is, I make this line longer, I make this line shorter, and vice versa. And so I'm always creating an equal potential on that line. And but it's really made out of how much blue and how much red. That's all it's really made out of. Is deciding what that profile will look like. And so there's nothing traveling. There's just how much red is hitting you versus how much green is hitting you. And that's all there is. There's no, there's nothing else to it. And so what's really happening with magnets is these lines are really just lines that are just telling something else that's capable of being turned a magnet. Atoms that are polarized, and they're just telling the atom to polarize to this object. It's stopping it from moving. You're spreading the iron filings on a piece of paper and giving them friction so they can't move into the magnet. So it's just basically arranged to the magnet. It's just saying it'll be compatible, not pushed away if it arranges so that the white side is closer to the red side is closer to the blue, and the red and blue are closer to each other. So it's an opposite magnet. And obviously, if I just stack a bunch of opposite magnets on top of each other, I end up creating another magnet here, and it's just an opposite magnet. Okay. And the trick is these lines. All of these opposite magnets that are created will be exactly the same magnet. Okay, they'll be arranged with the blue on top and the red on the bottom, or in this case white. And you can kind of see the obvious implication of that. I'm going to put an X in this, and then you'll understand this is the same and this is the same. That these would repel each other, and so that's why there's an empty space between them. So that's what the lines are being really created by. They're not lines of any direction or any force or any of that kind of thing. They're just really two charges, two light bulbs that radiate. One reflecting the red, one reflecting the green. And because of that simple rule of turning the greens and turning the whites, that's what they do. So you hit them with purple and they produce a segregation of the colors. So a magnet is just segregating the proton force and the electron force. It's just a filter Okay, so purple comes in, both forms of the force, and it just converts it into all red at one end and all green or blue out the other end. And now it will cause electrons to run away from this end, and electrons will run into this end, and it'll cause these effects. Now the only trick is that charge, all magnets are metal, composites that have metal in them. And metal becomes conductors. I can give lots of explanations, but the point is you can charge metal. Okay, so metals will become charged. So if I move a charge, like a big object that has an excess of electrons on it, a bunch of extra electrons, what will happen is that charge will affect the surface of the metal, and it will charge. And as the magnet surface charges, the filter breaks. So then the stuff that was coming, the green stuff, now is going to end up reflecting back, and the magnet's not going to be a magnet anymore. The filter is clogged, however you want to look at it. So charges break magnetism, native magnetism. Magnetic metals can't survive being charged, and the magnet loses its function as a magnet over the surface that's being affected by the charge. So when it's being bombarded, essentially by reflected force, it can be affected. So if you hit it with a segregated force from a charge, the metal will charge, and it'll essentially just break the magnet. So that's a more complex subject, and has, again, you got to go back to the atoms that are actually causing the mechanism to fully understand that. But it just explains why in certain circumstances you can't use a magnet to push a charge, even though it should theoretically push it. It doesn't, because it's not working as a magnet anymore. It's lost its ability to produce the extra electron force or the extra proton force needed to push or pull. Alright, so the basic point is that it's all straight line force. So it charges in Maxwell's equations. There's, they call them, somehow it's supportive of a wave theory, but it's really not. Faraday and Maxwell knew full well of this inverse square law, that the charge, is basically just radiating a straight line force, and that you could pick a point, equal distant from the charge, and it'll be the same amount of push at all those locations, because it's basically like a light bulb. If I go 3 feet around a light bulb, I'll get the same amount of light over here as I'm going to get over there, as long as I'm the same distance from the light bulb. And so this really is a straight line force. It's not waves of stuff. It's not any of that kind of stuff. They're rays that, the further away you get, the fewer rays that'll hit you, and you can just do a calculation. The mathematics is completely dependent on this idea of just, you want to say the force is 10, you just create 10 lines, of force, and you can fully understand how many of those 10 lines can hit you from here, or how many of those 10 hit you from here, or how many of the 10 hit you from here, and you can do all the mathematics to figure out exactly how much force the charge has. So this idea of a radiating point works perfectly in terms of fitting all of the mathematical theory. It's the mechanism. And so again, the argument is that when you're thinking of magnets, it's really the same thing. You're just really doing straight line force mathematics. And so if you want to know what the magnetic field is over here, you just calculate the distance from the two sources. You can average it, and you just calculate the contribution made from the two sources, and you'll know exactly what the magnetic potential is at that distance. It has nothing to do with any swirling lines or any of that stuff. It just has to do with straight line vectors, and the inverse square law are other laws of proximity. So obviously when you get to charges, you don't have the same problem of spreading in both directions, and so you can have R rules where it's only half the distance, half the force. You can have R squared rules, okay, half the distance 4 times a degrade in the force, or 4 times an increase in the force if you just half the distance you are. Or you can have R cubed rules, which magnets end up creating, because the further away I go from a magnet, the more purple it gets. So when I'm up close, I can see the difference between the red and the blue. But you can sort of understand as I get further away, and even if I did this with light bulbs, I put a red bulb next to a blue bulb, from a distance I'm going to see purple. I'm not going to be able to see the red and the blue, because the two are going to mix. There's going to be blue stuff going this way, there's going to be red stuff going this way. And so obviously the further away I get, I'm going to be back to 50-50. I'm going to be seeing just as much of this bottom as I'm going to be seeing of the top, and it's going to look purple. But up close, I'll just see red from one direction and purple from the other direction. Blue from the other direction. So that would be an R cubed rule, because the force is mixing as it's spreading. So it's doing the R squared thing. It's spreading in both dimensions, but it's also diluting with distance. And that is mixing. And the more it mixes, obviously you have more mixing angles. The further away you go, there's more angles where you can mix the two. And so the mixing adds the extra R and makes an R cubed rule. Now I don't know if that's ever been figured out to be exactly exact. I don't think anyone's ever properly measured it, so it might be an R 2.9 rule, rather than an R cubed rule. But anyway, close enough. But they're all just straight lines. So you want to do any figuring of the force and how strong it is, you just draw straight lines from the sources, the origins, and you will get the answer to your question. So there's no need for any notions of waves, and there's no need for any explanation for where the energy comes from. The energy comes from the universe. The universe is pushing things together. There is no elemental pull. An elemental pull is it's a paradoxical, impossible kind of thing to even imagine or describe as a physical event, because you have to create some kind of mechanism that can jump behind something and push it, because there just is no other way to do it. There's no way to make a mechanical pull. The universe is based on force that has only one direction. Okay, I'm moving in a direction, and I can hit you and force you to move in that direction, or to move in some other direction, but I'm going to force you to move, and the movement's going to be away. I can't hit you and make you move towards me. So there is no pull mechanism. There's no physical way to describe it elementally. It doesn't make any sense. It breaks the whole notion of momentum. So you really do have to understand that the universe is pushing everything together, and you create that effect by, in some way, degrading, moving a force that would be balancing. So if I take away the stuff going here, then obviously this thing will go this way. But nothing generates energy. Everything's just reflecting it. And the point is that one kind of matter reflects red, the other kind reflects blue, and it redirects the opposite color. The red thing redirects blue, and the blue thing redirects red. And understanding that, you can understand how a magnet can be created that filters and creates, segregates the two forces. And when you segregate the two forces, you can more effectively move electrons and protons, because you're hitting them with a force that only moves them in one direction. Alright, so that's probably enough. Without getting too complicated. So electricity is really just about making, when electricity moves through a wire, it makes it temporarily, it makes atoms, it polarizes atoms, it makes them into little magnets. And so that's how you convert electricity into a magnetic field, is that you're actually converting the metal into magnetic atoms while the electricity is going through the atom. So while the electrical potential exists, it means the atoms have to misshape. By misshaping, they turn into magnets. They create a magnetic field, and you can control that magnetic field by coiling a bunch of wire. You can maximize that field that's being created and create a synthetic magnet that only lasts while you're pumping electricity through the atoms and changing their shape. So changing the shape of an atom is what changes its ability to filter force, and when it can filter force, then it can affect electrons and protons. So when it can make the light red or make the light blue, then it can change how electrons and protons act. If it just makes purple, it won't affect electrons and protons in any overt way. So it's just about changing the environment, changing the field force, changing what's hitting things from in the environment. And some changes will make visible effects, and some changes will be too insignificant to make a visible effect. I mean, we're being hit by cell phone energy, but it's such a small number of the total photons we're being hit by, it can't push us anywhere. It can't move us around. But it is affecting our little electrons and protons. They are getting moved around by it. They are getting heated by it. All movement is a kind of heat, and all movement, in a sense, creates gravity in the end, so it all connects. But that's a separate subject. So anyway, it's probably enough of a statement. Probably have to redo it. I just, I wanted to emphasize kind of clearly that it's all straight line force. Straight line force fits all of the mathematical models. There's no model of a wave or vibrations or any of this other kind of stuff that you can't make, that you can't illustrate as just being vectors of straight line force, little bits flying through space, hitting another thing from a direction. It can all be understood, just like that circle looks like a wave. You could say, oh, it looks like a wave of soldiers, but it's not a wave of soldiers. It's a wave of individual men who went from point A to point B in a straight line. And so, yeah, they all went from the warehouse, and then we said, go out to the front, and you'd be 10 feet apart when you get to the trench. And so they all went out in straight lines to their little 10-foot apart place. And yeah, it could look like a wave of soldiers, but it's not a wave. It's not a vibration in a medium. It's real pieces of momentum moving through empty space. The empty space that isn't got electrons and protons in its way. Yeah, something like that. So anyway, we'll call that a video, and move on to other subjects and such. You should start with the Start Here video, I suppose, which does cover some of this redundantly, but some of it has to be redundant, unfortunately. Yeah.